Hey guys, I have a fun little video for you to see here. It's a video within a video, and it's going to introduce the difference between mass and weight. And if you've ever wanted to be an astronaut and go to space, this video might inspire you to pursue that as a career.
Hi everyone, my name is Nicole Stott and I'm a flight engineer with Expedition 20 on the International Space Station. And we're here today with you on the International Space Station and the Japanese Laboratory Module.
Hi, I'm Bob Thirsk. I'm also a flight engineer aboard Expedition 20. The topic for today is weight versus mass, a heavy-duty concept.
So what is weight? Weight is the vertical force exerted by a mass as a result of gravity. Weight also means the strength of the gravitational pull on the object. That is, how heavy is it? Weight is dependent on gravity.
On Earth, in a 1G environment, an astronaut in his spacesuit would weigh 360 pounds. On the Moon, in 1/6 Earth's gravity, the astronaut would weigh 60 pounds. In orbit, he would weigh 0 pounds because weight is dependent on gravity and the effect of Earth's gravity is not observed.
Using more physics and mathematical terms, weight is defined as the force with which a body is attracted to Earth or another celestial body, equal to the product of the object's mass and the acceleration of gravity. So in equation form, gravity equals mass times acceleration due to gravity. On Earth,
What they're saying to write this in equation form. It's the force of gravity. So write this down here. So the force of gravity is equal to the mass of an object times g. So this is a really good equation to add to your equation sheet. The force of gravity is mass times the acceleration due to gravity. To see this in action, the force of gravity on a 10 kilogram object is equal to 98 in the units of force, which are newtons. So 98 newtons.
8 meters per second squared.
Well, what is mass? Mass is the property of a body that causes it to have weight in a gravitational field. The mass of an object is not dependent on gravity. Mass is the amount of matter in an object. Bodies with greater mass are accelerated less by the same force.
If we use the same force on these two animals, the elephant, which has a greater mass, is affected less than the mouse, which has much less mass.
And what is gravity? Gravity is a force that governs motion throughout the universe. It holds us to the ground. It keeps the moon and the station in orbit around the Earth, and the Earth in orbit around the sun. It is best described as the attraction between any two masses, most apparent when one mass is very large, like the Earth. The acceleration of an object toward the ground caused by gravity alone near the surface of the Earth is called normal gravity, or 1g. This acceleration is equal to 9.8 meters per second squared, or 32.2 feet per second squared. If you drop an apple on Earth, it falls at 1g. If an astronaut on the space station drops an apple, it falls too. It just doesn't look like it's falling. That's because they're all falling together. The apple, or the onion, the astronaut, and the space station, all falling together.
Well, what is microgravity? The International Space Station and us astronauts aboard are traveling at approximately 28,000 kilometers per hour, or 17,500 miles per hour. And we're essentially falling around the Earth, creating weightlessness. The weightlessness that is felt in free fall on a ride at an amusement park or on the International Space Station when it circles around the Earth is microgravity. Objects in a state of free fall in orbit are said to be weightless. The object's mass is the same, but their weight would register 0 on a scale. Weight varies depending on if you're on Earth, the Moon, or in orbit, but your mass always stays the same. The first thing that Koichi and I would like to do is demonstrate that we're actually on board the International Space Station and we're in a weightless environment. So let us show you a few little tricks here that will make that point. I'd like to have an arm wrestle with Koichi. Let's see what happens.
I'm going to pause the video here, and what we're going to see, or what I want you to make a prediction of, is what's going to happen when the two astronauts have an arm wrestle. So I want you to think back to the last video, make a prediction, and then we'll talk about what we actually see happening.
Okay, here we go. Float. This is great, actually.
So what you noticed is that both astronauts flipped. And we can go back and talk about this. Let me roll this back.
An arm wrestle with Koichi. Let's see what happens.
Okay, and at this point, you see that this astronaut is applying a force on this astronaut, on his arm, right? He is pushing on him. But Newton's third law, here it comes again. Says for every action, there has to be an equal and opposite reaction. And so the reaction force is that this astronaut pushes back on him. And so they both are going to exert a force on each other, and therefore they'll turn. Now, can you tell based on how fast they turn which astronaut has a greater mass? In other words, if the force is equal, which Newton's third law shows us that it is, an equal force on these guys will not affect them the same because they have different masses. The man that turns faster, is he going to have a greater or lesser mass? If you said he's going to have a lesser mass, you're correct. So let's see who turns faster here.
This is great, actually. Okay.
So it seems like this astronaut has a lesser mass than this astronaut. But they're going to do one more demo for us to help us see not only Newton's third law, but the difference between mass and weight.
One of my favorite Japanese sports is sumo wrestling. We're going to try to sumo wrestle.
That is super.
So let's watch this again. And again, we're going to see here is a force equal and opposite. This astronaut goes back much faster than this astronaut. So equal force gave him a greater acceleration because he has lesser mass. Okay, so this video helps illustrate the difference between mass and weight.
This summer.
And hopefully this makes you, this type of video wasn't possible, 5 years ago. But it's only now that we're in space and video cameras are ubiquitous that we're able to kind of see this kind of science, physics in action. So I hope you enjoyed it. Let me know if you have any questions. And that's the difference between mass and weight.